Inverse trig functions. We need to recognise the graphs and the domain and range of the graphs of inverse trig functions and know the difference between the notation between inverses and reciprocals. We already know what we mean by inverse trig functions. We've used them a lot for a number of years. If we want to find the x when sine x equals minus 0.5, we simply use the inverse sine function, sine minus 1 minus 0.5. We get one solution. There's actually an infinite number of solutions. We get the principal value. And hopefully you're familiar with this. We're now going to look in a little bit more detail at what these inverse functions are and what their graphs look like. Firstly, let's just clarify the notation. We use the term f minus 1 of x to denote an inverse. But with trig it does get a little bit complicated. When we say sine squared of x, we mean sine x all squared. But when we say sine minus 1 of x, we mean the inverse sine. For the reciprocal, we would have to write sine x to the minus 1, like that. So sine minus 1 of x, or sine minus 1 here of 0.5, means the inverse sine, whereas sine x in brackets, the minus 1, is the reciprocal, in other words 1 over sine x. I know it's confusing and it's perhaps a little contradictory, as with powers like sine squared it means something slightly different, but unfortunately that's the notation we have to live with. So that means 1 over sine x. This means the inverse. Right, let's have a look at the sine graph. Hopefully a very familiar graph to you, y equals sine x. It's a many-to-one function. We've got a lot of x values which give us the same y value, of x values that would give us that particular y value, in fact any y value. So it's many-to-one. And there again we can see how different x values are giving us the same y value. With an inverse we can't do this. A many-to-one function gives us a one-to-many inverse, which we're not allowed. One-to-many isn't a function, it fails the vertical line test. So in order to take an inverse of the sine graph, we will have to restrict the domain. What domain could we use? Ideally, we want every y value with no repetition. So all the y values without being repeated. And hopefully you spotted that for yourself. If we go between minus pi over 2 and pi over 2, we achieve just that. Between minus 90 and 90, or minus pi over 2 and pi over 2 in radians. So that's it. That's the part of the sine graph we use to find the inverse. Okay, it's better in radians because as you can see the scale's similar. And we've got the scale here going from minus 1 to 1, so we get all of the y values and the x values between minus pi over 2 and pi over 2. If we draw the line y equals x, as we know, the inverse is the reflection in the line y equals x, and we can see the blue curve there. So what values are we going to have here, 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 and here? What's the domain and range? Well, as we know, the domain of an inverse is the same as the range of the original function, and vice versa. So the domain of y equals the inverse sine of x is between -1 and 1. X is greater than or equal to -1, less than or equal to 1. And the range is between -π/2 and π/2, including those 2 points. There we are. So that is the graph showing the inverse sine of x. And we can see there that the gradient is always positive except at the points where x equals -1 and +1, where it's undefined. We sometimes use the term arcsine. It's a little bit dated and unlikely really to crop up. But if you do see the term arcsine, it just means inverse sine. So arcsine AX is the same as inverse sine of AX. And there's the graph there, alongside the sine graph. Okay, time for you to have a go. I'd like you to have a go at doing a similar exercise with y equals cos x. Think of a suitable domain, sketch it, write down the domain and range, and anything you notice about the gradient. And then once you've done that, see if you can do the same for the inverse tan of x. Pause the presentation and have a go. Y equals cos x. Well, it's this part of the graph we want between 0 and pi. We can't use between -π/2 and π/2 like we did with the sine graph, because we'll have repetition and it won't include all the y values. So with the cos graph, we go between 0 and pi, and that gives us all of the y values. If we then reflect in y equals x, we get this graph here, and that's our inverse sine graph. And you should be able to work out the domain and range in a similar way to what we did with the sine and the inverse sine graphs. You'll notice with the inverse cos graph that the gradient's always negative, again, except at the point where it's undefined. So it's undefined here where x equals what, +1, and here where x equals -1. Tan graph looks like that, and your knowledge of the asymptotes should tell you, well, we know for the tan graph we have asymptotes at -π/2 and π/2, so we can see here that at y equals π/2 and y equals -π/2 we have asymptotes. So we can have any x value, but the range just goes between -π/2 and π/2. Because they're asymptotes, it's not and equal to with the inequalities like it was with the inverse sine and inverse cosine graphs. Okay, if you've got through that and you've managed to have a reasonable stab at those graphs, then you should be prepared for the lesson. But have a look through, make sure you're familiar with them, make sure you understand this concept of them needing to be one-to-one and the restricted domain that we use.